Right, so yesterday we did heuristic 19, which was the cascading, the multiple effects evaporators. And now we are still doing separations involving solids, but we are looking at drying of solids. So yeah, we've got three different options for granular material. The first will be to use tray and belt dryers. That's for big particles. For in-between particles, 1 to 3 millimeters, small free-flowing particles, 1 to 3. A pneumatic conveying dryer. Oops, there are 4 there. Just writing it down because I'm going to go to a whiteboard to illustrate what these things are. So we've got, so let's start from the beginning. We've got tray and belt dryers. We've got a rotary kiln, a rotary dryer, discussed over here, rotary cylindrical dryer, and then pneumatic conveying dryer, and eventually a fluidized bed dryer. Now you're only doing the fluidized bed stuff now with Mr. Duplessis at the moment. Have you done that yet? Have you done anything on fluidized beds yet?
Not yet. We finished sedimentation this week.
Sedimentation, but have you done the fluidized beds?
No, not yet. We've only done batch drying and continuous drying. We still need to do fluidized beds.
All right, cool. Thank you. All right, so now I'll go over to the whiteboard. So we get back from share files. We share a blank whiteboard. And now the first one we're going to do is the tray dryer. So we have a bin. Which contains our wet solids. And that drops onto a belt. Oh, these are supposed to be circles, and they're all supposed to be level, on the same level. Okay. Now we have a belt, which means I must use a pencil, and I'll choose another color. Conveyor belts are usually black. So now it's testing my motor skills here. There's your black rubber conveyor belt. Well, it might not be rubber. You can have a mesh steel one if there's a lot of heat involved, and then you can have a radiating flame or radiating heat coming from the top here. So this could be a flame, or something like these gas heaters that heat up a surface, and like gas heaters in a home. It makes a radiating surface, and that will radiate heat onto the material. The material falls down onto this belt, and as the material moves along the belt, it gets dried, and eventually it goes down into another bin, and that bin I would say you can collect everything in the bin over here. What temperature would you go with a steel belt? I guess I think the issue is not the belt itself. The issue is going to be the bearing, the roller bearings. That will be a problem. So you can't go too high. So really, you wouldn't go much higher than 100 degrees C, because that would result in boiling of the water over here. So yeah, I think sort of 100 degrees C is going to be the as high as you would go, and even for 100 degrees C, you could use rubber. Okay, so that is the first one. So this is for 3 to 5 millimeter particles. 3 to 5, and that's pretty easy and straightforward. So you'd probably put this in some sort of a cage so that you don't lose your radiative heat, so that the radiative heat is reflected back into the onto the belt. All right, so that's the first one. The second one that they discuss is a rotary dryer, and I think I'm going to use lines. A rotary dryer looks something like this. Now I've got to use the pencil. And I could use an ellipse. Let's try it. I'll try an ellipse. Oh, yeah, that's fine. If I just use the pointer to select it. Oh, that's not quite fine. Put it there. Pull that one down. Oh, yeah. Now we're talking. Okay. So this of course is rotating. You get a pencil, and let's say it's rotating in this direction. And now you've got material that will come in from a bin. I'll draw the bin freehand this time. And it goes into the rotary dryer that way. Therefore, it will be, so therefore, what you get is let me go to another color. Get your material that's inside this rotary dryer that forms a bed of material inside, and that bed runs the length of the kiln. So as this rotates, a particle will move along the wall upwards until it gets to the top, to at some point where the angle is high enough that the particle can fall down, can roll down the surface down here and start again from the bottom. Now, what's good about that is on this surface you get radiative heating, and it is a continuously renewed surface. So that particle gets pulled up again to the top, and then it sees the radiation again. Moreover, the heat. So we're going to put in fire or hot gas in over here. So that's your flame. That's your flame going in there, and so the hot gas is moving this direction. Yes, that would be. Actually, no. You would usually do it. You would do it counter flow, as we normally use. Let me just see if I can catch these things. Oops. I'm going to just pull this flame and put it in this way. So the flame gas is coming in pointing in that direction. I'll give some more pencil marks to make the flame point in that direction. Okay. So the flame is coming in there, hot gas, counter current to the material movement, and then your gas saturated with water will be coming out on this side, or almost saturated with water. But anyway, the radiation of this hot gas will also radiate onto the walls of the tube of this rotary kiln, and the walls get hot, and then any particle that impinges against this wall and as this particle moves, oh, wait, pointer, as the particle moves along the wall, because the wall gets heated by the hot gas, it also gets heated, and as it rolls down, it has the opportunity to evaporate the water. So they work quite well. The problem is if the particles stick to the sides, you get what they call banding. So you get a whole big band of stuff that sort of blocks up the rotary kiln, and that sort of band, because the particles are sticky, it will just grow and grow in size, and there's no way to easily just knock off that band. It requires maintenance, needs shutting down the plant. So it only works really well when you have a non-sticky substance, non-sticky solid. So that solid should be able to roll freely as the particles get to the top, and be able to roll freely down the surface. Right. So that is for 3. Yeah, it's also for 3 to 5. In fact, you can do this for 1 to 5 millimeter diameter particles. It's quite. You can use a rotary dryer for many sizes of particles. Let's keep an eye on comments. Everyone, right? Okay, I haven't missed any. I've been getting notifications, and I always wonder if it's somebody asking a question. So that is the rotary kiln, and then I'm not going to move to another. Let me see if I can select everything here and move it a bit. Oh no, I can't. So I'm going to just draw underneath here. So we go back to drawing with a. I'll just draw with a pencil in blue and have a feed bin over here. And that drops into, well, you will have a rotary valve. A rotary valve is a valve that's got spaces, 4 spaces like that. And this slowly turns, it gets filled. As the empty space is at the top, it gets filled, and then it drops down the solids into a pipe. I'm drawing. Oh, now that's a vertical pipe. You can see that, huh? Gee. Touch screen. That's what I should be using. Okay, so that's a pipe, a beautiful round and straight pipe, and this is a. So we put in air over there, and we put in fuel over there, and that gets nice and hot. Let's call it 1,000 degrees C. So you got gas moving along this pipe, and you've probably got some idea of how fast you can run gas in a pipe, and a rule of thumb would be about 20 meters per second. You've got wet particles falling into this pipe and being pneumatically carried along the pipe. And as they're pneumatically carried, of course, you'll get flash heating of the particles by this very hot gas, a very good heat transfer, and therefore the particles will dry in the really small amount of time that it takes for them to move along here, and then eventually into, oops, I've got the text tool on instead of the pencil tool. And the pencil tool is to show a cyclone. I'm going to show a cyclone like this. Oh, that's an ellipse. These are parallel lines. I've got to actually explain to you what these are because they're so badly drawn. And there's an outlet for the gas coming off at the top. Yeah. So that is the wet gas without any solids. Now, in a cyclone, this sorry, let me go to. I'm just going to draw this inside the. I'm going to draw this inside. This pipe actually goes inside the cyclone a bit. Ah, yeah, man. Yeah, I really need a stylus and a touch screen. I've actually got a touch screen on my computer, so I must get myself a stylus, and this will go a lot better. Anyway, here particles come in. By this time they're dry. It's hot gas with dry particles, and this enters tangentially into this cyclone. So it creates a swirling effect, and you get centrifugal force on the particles so that they fall down the inside of the cyclone. Yes, Philip?
Sorry, sir. Would you mind using your cursor, please?
Thank you. At last you are reminding me, because I get so annoyed with myself when I forget. Right. So let's start again. Here are the particles and the hot gas. Dry particles and hot gas are entering the cyclone. These particles are entering tangentially, so they turn around inside the cyclone. They get blown in a circular motion, and the flow of gas will be downwards because the gas can only go up through this pipe. So it first has to go around, so it'll maybe do 20 revolutions by the time one of the gas molecules gets to here, where it can actually go up the tube. So that's why this tube extends a little bit into the cyclone. So the particles and the gas are going around in a circle, and in fact there's an entire vortex that goes right down to the bottom, and eventually the vortex is not as strong at the bottom, and the particles all just slide down to the bottom, and they can be collected out here. And the flow of gas is such that it actually goes all the way down and then up the vortex, and this is nice clean gas that comes out. And cyclones are very effective. But anyway, what I've described over here is a pneumatic conveying system, or pneumatic drying system. Wet particles coming in, flash drying extremely quickly, because if this is 20 meters per second and you've got 20 meters of piping, you can dry them in 1 second, relying on this extremely good heat transfer from the hot gas to the particles. If the particles are too big, that's why we talk about 1 to 3 millimeter particles. If the particles are too big, it will take too long for the heat to penetrate into the middle of the particle. So let's just put that in 1 to 3. Right, and then the other thing, you can see how very clearly I've marked this as a horizontal bit of piping, and this is a vertical bit of piping. Yes, this is a vertical bit of piping, because you can't do them at an angle. In pneumatic conveying systems, it will always be horizontal or vertical. With horizontal, you will get some stratification, but if you've got high enough and turbulent flow, you will get a denser area at the bottom, but it will not settle out. And then in a vertical, of course, that's easy enough, as long as the velocity of the gas is higher than the terminal velocity of any of the particles. So the terminal velocity of your 3 millimeter particles will be, let's say that terminal velocity is 18 meters per second. Then you've got to design this to be at least 25 meters per second flow, so that you exceed the terminal velocity of the big particles. And so there's another bit of horizontal pipe before it goes into a cyclone. And you have to have a horizontal bit of pipe before the cyclone, because a cyclone has to be mounted in a vertical position as shown. Okay. So there are dry particles coming out the bottom, and there's dry air, or well, wet air, wet hot air coming out the top. Okay, Philip.
So would we then try to minimize the horizontal piping sections in such a dryer?
Yes, you would. And again, you try and actually avoid elbows. It's not going to be an elbow. It'll be a very it will be a 90-degree curved pipe. Curved pipe would be a better description. Oh, sorry, where's my pointer? That is a curved pipe that goes around, because you're going to get erosion on the outer edge, where the particles are pushed against the steel, whatever your construction material is, and therefore you will always get erosion as soon as there's a bend. But for these particles to actually fall into the pipe, you've actually got to have a little bit of a horizontal section. As I mentioned, you've got to have a horizontal section going into the cyclone, but mainly you would want to use the vertical section, because the vertical section has the advantage that the biggest particles will be transported slower than the small particles. Small particles will be transported at the speed of the gas, and the big particles will be transported slower because of their terminal velocity in the gas. And that's good, because the bigger particles need a higher residence time for the heat transfer from the outside of the particle into the middle of the particle.
Yes, thank you.
So how do you clean the pipeline when, say, the power goes out? Well, the power won't go out. I mean, essentially, you've got a burner here. So if the power goes out, your burner will probably stop, and you'll shut off both your air and your fuel, and you'd stop the rotary valve from going. So I don't think it would be a problem. Any blockages in that respect. Even if some wet stuff did fall down, when you start up again, it will dry out, and you're going to design this pneumatic line that you've got high velocities that will push out. It's drying of solids is more important in South Africa than in other countries, because we've got a minerals processing industry. So it's likely that you in your careers might come across some drying problems. Yeah, that's it. Yeah, Jared, you've got the South African solution. Hosepipe is very useful for cleaning out gutters and things like that. Okay, and that's speaking from personal experience. So yeah, that's enough of that. Now, how do I clear the whole blackboard? Show view controls. No, that's not going to do it. There, rubbish, clear. Okay, so the last one after pneumatic drying is when you've got 1 to 3 millimeter particles. No, sorry, less than 1 millimeter particles. Less than 1 millimeter particles. You use a fluidized bed dryer, and that consists of, let's get a nice drawing, rectangle shape like that, and we do another rectangle over here, and we put in, well, let's draw another rectangle over here, and I'm going to go really smart and use proper lines. Got fuel going in to the burner. We've got air going into the burner. we've got hot air going into the plenum. Oops, into the plenum. Now, what the plenum is, it's a chamber. Okay, let's just first draw in so I want to use a pencil and gray. I want to draw in the fluidized bed. Okay, that's the surface of the fluidized bed, and yes, that was not because my hand was shaky. It is like a bubbling kettle. If you're boiling a kettle and your kettle is boiling, you can see those bubbles on the surface, and the surface is highly turbulent. That's exactly what a fluidized bed looks like from the top. If you look down on a fluidized bed, it looks like boiling liquid, except that it's sand that is bubbling. It's quite something, and you can put your hand in it, and it's a fluid. That entire sand bed is fluidized, so you can. It's as if you're putting your hand into water, except that it's got a higher density than water. So you will actually feel the buoyancy on your hand if you put your hand into this fluidized bed. So a fluidized bed is a bed of small particles, call them less than 1 millimeter particles, and you are bubbling gas. You are forcing gas through holes. There are holes in this plenum at the top that allow the gas to go through, and then you will get gas bubbles in the fluidized bed. Gas bubbles tend to get bigger towards the top. So bubbles tend to grow. They'll start small as they come out of these little holes in the plenum, and they tend to merge together in a fluidized bed. So you can't make a fluidized bed very deep. Probably the deepest you will go is about 1 meter, but 300 millimeters is more likely. So now let's go back to drawing with shapes in blue, because I haven't shown you where the wet particles are in a chute like that, and they enter into the bed over there. So there again, you probably have a rotary valve operating to let a certain amount go in, or actually more often than a rotary valve, you would use an auger, a screw conveyor. That is a tube with an Archimedes screw in that tube, and that will propel the wet particles into this fluidized bed. Okay, and then of course your hot gas will come out, and you go to a cyclone to remove any dust. Let me draw a cyclone there. Okay, so there you get dust, but you will take off your solids from the bed with an overflow from the fluidized bed, and those will be the main. That'll be the main thing, your dry solids, and then from here you can mix the dust that you've collected back into the solid material. And that's about it. So this might be operating at 1,000 degrees C, like in the previous example. Oops, 1,000. 1,000 degrees C over there. But as soon as it enters this bed, it sees the cooler particles let's see that. As soon as this 1000°C goes through these little holes, it goes immediately into this fluidized sand and sees a great deal of surface area in the sand. And so within a few millimeters, that hot gas can go from 1000 degrees to whatever temperature you're operating your fluidized bed at. Let's say we're operating this fluidized bed at 110 degrees C. So it will very quickly go from that 1000 degrees C to 110 degrees C, and all of that energy, the sensible heat that's in the gas, in these hot gases, will be transferred to the bed, and that sensible heat will do the latent heat evaporization of the water, and it will also be heating up these particles, these wet particles. It'll be heating up the particles themselves. It'll be heating up the water, sensible heating, up to 110 degrees C, and the latent heat evaporization of water will also be involved. Oh, sorry, will also be involved in here. So we've got, let's just think of the solid particles. The solid particles, 25 degrees C, they must go to 110 degrees C, sensible heating. We've got water, because the particles are moist, that must go from 25 degrees C to 100 degrees C, latent heat evaporization of water, the boiling of the water, and then further heating of that water vapor to 110 degrees C. So everything that's coming out here, a fluidized bed is very well mixed, so you will have the same temperature everywhere throughout this fluidized bed, and the gases that are coming out here will also be at exactly 110 degrees C because of the excellent heat transfer you get in a fluidized bed. So this stream coming up here is 110 degrees C, that stream is 110 degrees C, this stream is 110 degrees C. And then you're losing gas. So it's not very inefficient because you had 1000 degrees C and you're letting it out at 100 degrees C instead of ambient, which is 25 degrees C. So you're not losing a lot of energy doing your drying in a fluidized bed dryer. So if your the particles have to be loose. If they're cohesive, you will not get your bed to fluidize. And if they're too big, it will also not fluidize. So you need to, when you have particles that are not cohesive and less than 1 millimeter in diameter, or less than 2 millimeters, even in some cases, it depends on the density of the particles. Then it is probably a good idea to use a fluidized bed dryer because it is fairly efficient and easy to operate. So that's it. Those are the things. Let's go back then to the PowerPoint presentation. Share files. Share. And we are down at heuristic number 20. Yes, that's what I want to show. Please show it. Thank you. Right. Now we can go through it and maybe you'll understand a little bit better. For granular material, free-flowing or not, particle sizes 3 to 15 millimeters, use continuous tray and belt dryers. I didn't mention that where I showed that belt, it could have been trays on a belt, or trays that are connected together, and then the trays tip over at the end of the belt, essentially. With direct heat, you can use radiative heat from the top. For free-flowing granular solids that are not heat sensitive, use an inclined rotary cylindrical dryer where heat may be supplied directly from a hot gas, which I showed, or indirectly from tubes carrying steam that run the length of the dryer and are located in 1 or 2 rings concentric to and located just inside the dryer rotating shell. Yes, Philip.
So would we not rather use the rotary dryer if the material is heat sensitive? Because using a flame directly on the heat sensitive material will also be bad.
Yes, that's why they say for solids that are not heat sensitive for the rotary, because that's when you're using a flame. But I reckon if you're using steam tubes inside the dryer, it's mechanically a little complicated, because you've got to have the steam must rotate, so you've got to have a seal where the steam can enter the thing. So I don't really like this idea of having the steam hot gas indirectly from tubes carrying steam. It's unnecessarily complicated, but at least with the steam you will not have too much. You could probably get away with not such temperature sensitive materials.
So would we then rather use the continuous belt drying if something is sensitive to heat?
I wouldn't. If possible, I would go with the fluidized bed. But now, if the particles are large, and heat sensitive, I'm not too sure how I would go about it. Because of the belt dryer, the tray and belt dryer, well, a tray dryer will be fine, because you can put it in a large oven, and in fact, I think that's how they do it. You can put it in an oven that is, at a low temperature, at 100 degrees, less than 100 degrees, warm air, in other words, this 60-degree air, dry air that's flowing through, and the stuff moves very slowly in trays, or even in cocoa pans, little rail cars move slowly through the oven. Let's call it an oven, where the temperature is low enough that it never affects the heat sensitive material that you're trying to dry. So yeah, these are heuristics, and every which are going to cover most of the types of situations that you come across. That's every situation is different, and then you've got to start making a plan about how you're going to deal with that situation. So heuristics don't cover every single situation. When we started talking about heuristics, we said you must look at the situation for every single case. These just give you a first guess at what you should be doing.
All right, thank you.
Can we move on to heuristic 21? For pastes and slurries of fine solids, use a drum dryer with indirect heat. For a liquid or pumpable slurry, use a spray dryer with direct heat. Okay, a drum dryer, I'm going to draw on this slide because I've got plenty of space to work with. A drum dryer, I want a circle, which I hope is not going to come out as an ellipse. I see it's coming out the wrong place again. But, okay, there. Wait, I'll just move it again. All right, so let's say the drum dryer. The drum dryer is heated on the inside, and you can use steam or electrical heating on the inside of the drum. You would put in a let's think. You would put in your no. All right. This is my bin. An artistic bin, and that is the paste is pushed against this drum, and that causes a cake to form. And let me just draw the outside of the cake, but then I've got to follow this drum very carefully. So it's on the outside of this drum. It's much more even than I'm showing it. And eventually you get to a scraper, and that scraper will scrape it into another bin. Okay, so we've got an arrow going in that direction. Drum is slowly rotating. It's been heated from the inside. That is where we call it our indirect heat, because the heat is not touching the solid. The solid, oh, I hate this. No, I hate that one. Delete. Just need to fix this. It's unacceptable. Okay, so there's our bin. There we go. It's a better bin. And the solids are stuck to the bin. They're getting heated with indirect heat across this steel shell. And by the time they get to the other side here, they are dry and they could be scraped off, and they fall, the dry stuff falls into this bin. Okay. And then, of course, you're going to design this the way it gets pasted onto the drum. Let's call it a paste or a slurry. You will design that so that the little shell of material that's going around here is thin enough that by the time it gets to the end of this rotation, it is already dry. If you make it too thick, you're not going to get enough heating right on the outside, and essentially it won't be dry enough. But essentially, this sort of drum dryer will need a temperature on the inside here of higher than 100 degrees C, because you will need to boil the water. It will be coming off as steam rather than as an evaporated water. Right. So that's a drum dryer. For a liquid or pumpable slurry, use a spray dryer. Okay, so the spray dryer, let's think how I'm going to draw this one. Okay, I'll use a rectangle. And at the bottom of the rectangle, I'll use lines. Oops, at the bottom of the rectangle, I'll use lines. Where we take off the dry coffee. Okay, I'm saying coffee because this is the way coffee is. This is the way coffee is dried, and we've got hot air coming in this way. I can use lines again. So there's our hot air coming in, and we've got hot wet air going out the top here. Now I've drawn it to the wrong place. We've also got, let's go for a different color. We've got our stuff, our slurry coming in over here and being pumped in. And there's a very specialized spray. And this is the secret of unit operation design here, is there's a spray ball that makes droplets of exactly the same size, because usually your coffee granules, you want to have all of your granules about the same size. So if you look at old coffees like Frisco, that is a powder, and then they use a different drying method. But these most coffees that you buy now, I think some of them use freeze drying, but those are the more expensive ones. I think something like a Rick coffee will use this sort of drying. So you make little droplets from the spray ball that are exactly the same size, and therefore as the droplets evaporate, as they fall, oh wait a minute, pointer, as the droplets come out of the spray ball over here and they fall down, they are continuously drying, they're losing their water, counter current to this hot air that's coming in and rising up through the spray dryer. So if these droplets are all the same size, then you will tend to get the same size of particle at the bottom here. If you have droplets that are too small, they can be carried out as powder with the gas at the top there. If you have droplets that are too big, they will fall too quickly, and then you might have some liquid, some water. They might not be properly dried by the time they get to the bottom. So yes, as soon as you have a spray dryer, it's the critical part of the thing is your sprayer, that it gives even sized particles. So that's why they talk about a liquid or pumpable slurry coming in over here. Because if it's a pumpable slurry, you can still use a spray, but you might have a different design for a liquid compared to a pumpable slurry. Okay, so that's spray drying. Because this upward velocity cannot be too high, you tend to find that these things are enormous. So you're talking sort of 5 meters in diameter and 10 or 20 meters in height. So that you've got a slow, big diameter, so that you've got a slow movement of the hot gas coming upwards, and the large heights that you've got enough residence time as the particles move downwards, and you must be sure that they're dry at the bottom. Right, and that seems to be enough for today. Heuristic 21. So we'll carry on with Heuristic 22 after the mid-semester break. So I'll see you on Friday, where we'll have our next DW Sim TUT, and then we'll have a week's break. Any questions? There we go. There's a comment. Okay, thank you. Good. All right, so I'll switch off the recording, and I'll see you on Friday.